Hi everybody, I'm the greatest living inventor, and today we are doing my invention, cancer placenta symbiosis. So let me write it down. Cancer placenta symbiosis. Okay, so it's the third time that I'm doing this, so I need really to rush through it. All the links to Wikipedia and so on will be in the video description, so I'm not explaining almost anything. Okay, so it's only 8 pages, but it's really dense. Okay, fighting cancer spread by relocating the original tumor into a controlled environment in our body and harvesting the special proteins that prevent the secondary tumors from starting. Proteins which the primary tumor produces naturally. This is a solution against all kinds of cancer. It's based on symbiosis instead of eradication. The advantage of my invention over the original approach is that we don't need to know which proteins are needed, how to produce them, how much of them to inject the patient, and when. The original tumor does all that for us. With this invention, we are paying with electrical/mechanical complexity, and in return purchase biochemical/medical simplicity. Since we have more understanding in the first ones, I think it's a good deal. Background. My invention is an extension of the invention of Dr. Judah Folkman, the genius who invented a prototype pacemaker and a drug-releasing implant. My invention is an extension of Folkman's greatest discovery, angiogenesis. So Judah Folkman, Dr. Judah Folkman. Okay, he's a genius, but I don't have time to explain. You will see in Wikipedia. And his greatest invention, he had many great inventions, but his greatest is angiogenesis. Angio means blood vessels and genesis means beginning. Angiogenesis means that cancer tumor releases chemicals that tells our body to grow blood vessels and feed the tumor. Also, the small pieces that break off from the primary tumor are seeds, seed like a plant seeds, for the secondary tumors, the metastasis. But Folkman discovered that as long as the first tumor, the original tumor, is active, it releases to our blood special proteins, inhibitors, that prevent these seeds from developing. Basic idea. Cancer behaves like a separate animal. It no longer accepts that it's a part of the same animal. The cancer tries to exploit as much resources as it can from the host animal, the patient, host, inside which it grows. So we need to look for a situation where a parasite is restrained or moderated successfully. We have such a situation with a fetus in the womb of his mother. So I'm not drawing, I drew the mother and so on. I'm not drawing anything. I'm just explaining verbally. The baby's cells also keep dividing. The baby's cells also keep dividing and the baby grows, but we don't see it as a danger. This is because together with the fetus, the body develops a placenta. Placenta. Okay, it's like you can see placenta in Wikipedia. It's something with a lot of blood. There is the baby side. Here is the umbilical cord. And this is the baby's side. Of the placenta. And this is the mother's side. The baby's cells also keep dividing, and the baby grows, but we don't see it as a danger. This is because together with the fetus, the body develops a placenta. This is made of two parts. One is the side of the mother, and one is the side of the baby. The main idea is that each of these two parts have its own blood, and they don't mix. It's like a filter. Okay, this is a filter. The whole placenta is like a filter. Small molecules like oxygen pass between them, but pathogens can't. Okay, so if we have an oxygen molecule, it can pass to the baby. But if we have a bacteria, it cannot pass. Okay, it's too big. These holes don't let it pass. So it doesn't pass. The mom can have bacteria, but the baby no. Pathogens cannot. This is the same idea as compartmentalization. Imagine like when you run a software inside a sandbox. Okay, the program runs and thinks it is touching the operating system, but actually it's not touching the it's just touching the sandbox. Okay, so in computers, I'm not writing, it's like a sandbox. Okay, I'm writing sandbox. Okay, in computer. And the operating system is protected. Now, an important part to mention is how cancer kills. It kills either physically by inflating inside something crucial, like our lungs or our brains, or by secondary tumors, metastasis. Metastasis. It's one word, metastasis. It's a secondary tumors. Or by secondary tumors, metastasis, that inflate in these crucial places, lungs or brain. This is how cancer kills. What does this mean? This means that if we just had cancer in a non-critical place, not here or here, we could prevent it from making secondary tumors, metastasis. And so if we, what does this mean? This means that if we just had cancer in a non-critical place, and we could prevent it from making secondary tumors, metastasis, then it will not kill us. add to this one of Judah Folkman's discoveries that a cancer tumor prevents other tumors as long as it's active. So our plan so far goes like this. I'm not writing, I'm just telling. 1. Take out the dangerous tumor from where it's now, like lungs, for example. 2. Put this tumor back inside our body, but in a non-critical place and in an isolated way, filtered by placenta. How is the time? 11 minutes. Okay. 3. The tumor releases small proteins like endostatin, okay, so they can pass because it's small proteins, which enter our blood and stops secondary tumors. Big cancer cells, okay, if there is something bad, big cancer cells cannot enter into our blood. They cannot pass the placenta filter. 4. Make a mechanism that reduces the cancer tumor but does not kill it. Keep it active but small. So we cut little pieces of it, like we keep it small. Each time we cut half but not all of it. Okay. How is this done in practice? As for step 1, radical surgery to remove tumors is performed routinely. The problem is that following this, the secondary tumors, the metastases, appear. But we deal with them in the next step. So on to step 2. What is a non-critical place? Okay, non-critical place. Or non-critical organ. I think the appendix is the best candidate. Okay, so appendix. I think the appendix is the best candidate. Sorry. This is because until 2007 it was considered absolutely unnecessary in humans. What's more, if you have it, there is the appendix in your body, there is always the danger of it getting blocked and suffer appendicitis. Okay, appendicitis is the inflammation of the appendix. It's a problem that an emergency that you have, and then you have to remove it. According to Wikipedia, it's very common, appendicitis, and then the doctors remove the appendix and you are good as new. So in Wikipedia you can look in appendicitis, uses of the appendix as a pipe. Appendix as a pipe. So uses of the appendix as a pipe can be seen here. Wikipedia, appendix, anatomy, surgery, in the section about surgery. There are 2 real working examples in Wikipedia of appendix as a pipe. The first example talks about getting liquid outside of the body, getting urine out through the navel, which is a Mitrofanov procedure in people with neurogenic bladder. The second example talks about getting liquid solution into the body to wash the colon in children with paralyzed bowels or major rectal sphincter problems. We will discuss both options. I'm sorry I'm not writing everything. It's the third time I'm doing this invention. Okay, 15 minutes. Option 1, out through appendix. So I'm erasing everything. You can see all of this in the in appendix, and then appendix, anatomy, surgery. Okay, so appendix, anatomy, in Wikipedia, and surgery. So you can see both options. Okay, now I'm talking about the first option. Which is out from our body through the appendix. So remember the placenta. Okay, mom side, baby side. Okay, so option 1. Now we are talking about the invention. Option 1, out through appendix. Let's write appendix in brown because this is how we wrote it in the beginning. Okay, so everything we talk about now is about this out of our body through the appendix. Ideally, we could use the appendix as a pouch, like a bag, to hold the cancer lump. But there are rare cases when the appendix gets cancer, and we don't want that. So in Wikipedia, appendix cancer. Okay, so we will use the appendix only to hold the dead cancer cells, that part of the tumor that we kill after we killed it. The placenta has two halves. The baby half, which is the fetal placenta, chorion frondosum, which is connected to the umbilical cord. Okay, the baby side. The umbilical cord goes to the baby's belly button. And the mother's half. The other side of the placenta is the mother's half, maternal placenta, decidua basalis. Imagine it like a pipe with a sponge and then another sponge. Okay, so now we have the placenta, which it's like a sponge and another sponge. And in between them there is a filter. And here is the umbilical cord. Okay, this is the baby side. And this is the mother side. Okay, so this is the placenta. And now everything we are talking about is inside the appendix. The appendix is all around us. Okay, this whole thing is the appendix. Okay. Okay, so the appendix also gets blood. Okay, there is blood vessels coming into the appendix. This is one pipe, this is another pipe, and the umbilical cord has inside blood vessels. This is one and this is two. And we connect them. Okay, so we connect this and we connect this. So this, one of them brings fresh blood into our system, to the cancer. The cancer will be here, the tumor. Okay, here is the tumor. Can you see what's written in green? Yeah, okay. So this is blood going in and blood coming out. Okay, blood going in, blood going out. And this is the umbilical cord. Okay, well, up to a point this is the umbilical cord, and these are blood vessels that are coming from outside the appendix. Okay, so the appendix, let's say, is up to here. And blood vessels coming to the appendix normally to feed the appendix, but we are using them to feed the cancer, but not directly through the placenta, because we don't want the cancer to give us cancer in all our body, just to be here and give us the small molecules that Judah Folkman discovered that they protect us from secondary tumors, from metastasis. Okay, so I hope it's clear. Since we want to keep the appendix alive, this is all thing the appendix, and fed with blood, both in and out, we will connect the ingoing pipe is this appendicular artery, and the outgoing pipe is this appendicular vein. The umbilical cord contains two arteries, the umbilical arteries, which are outgoing pipes, and one vein, the umbilical vein, which is ingoing pipe. So we connect this accordingly. In Wikipedia you can see this in umbilical cord. Okay, this purple thing, so remember this is the umbilical cord, what goes to the baby's belly button. Okay, navel. Okay, so but this is no longer in the mother, this is now in the patient. In the patient that suffers from cancer, we took out the cancer from the lungs or the brain where it's dangerous, and we put it inside this appendix system. The umbilical cord contains, oh sorry, I read it already. Okay, what we do is we switch the two halves of the placenta. Okay, so normally we have, well, I just read. What we do is switch the two halves of the placenta. The sponge, mom's side, is placed on the tumor because the tumor can interface with it. Okay, there is a potential of cancer in the placenta, so this cancer can touch this, can feed on this. It's the placenta cancer is very rare. We don't want the placenta to get cancer itself, okay? And it's very, very, very rare anyway. There is almost no cases of placenta cancer. What we do here is this can interface because it's a rich, it can feed, take blood and blood in and blood out from the placenta. This is what I mean, okay? It's not infecting this placenta with cancer, it just feeds. It can interface in give and take with the placenta. It's rich with blood and nutrition. Okay, the sponge, mom's side, is placed on the tumor because the tumor can interface with it, and the sponge plus pipe, the baby's side, this pipe umbilical cord, we connect to the pipes that go in and out of the appendix. All this is the appendix. Okay, what time is it? 27 minutes almost. Okay, as we said before, the tumor cannot be in the appendix or it will infect the appendix. So like this, it's not good. It will infect the appendix. So we need to put the tumor inside some container. Okay, so we want the tumor inside something. Container. What kind of a container? For this, we need to think, how do we reduce the tumor? Remember, we said we want to cut it down, so how do we do this? I think the best way is by ablation, which means cutting it with burning heat. So I'll put the link, radio frequency ablation. I'm not writing everything because that's how I got stuck with the time. So radio frequency ablation. So one possible way is external. Someone, a doctor or the person itself, will periodically insert a needle-like RFA probe. Okay, so we put a probe from here through the belly button, like this is the belly button of the person. We cut it, we make a incision, and we put inside the belly. This is the person. We are inside the person. This is the belly button here. Okay, this is the navel. Or belly button. And we put this hot thing, and we only activate it after it's inside. Okay, we can do this. It's electric. We can only activate this part once it's inside. And then we don't kill the whole tumor, but we kill half of the tumor. Okay. So a needle-like RFA probe through the hole in the navel, or the place where we made the opening leading into the appendix, pass it through the appendix without activating it yet, as to not hurt the appendix, not to burn, and then when it's deep enough to be in the tumor, activate it, the tip. Okay, so in Wikipedia, radio frequency ablation, hashtag tumors. This means that the container needs to be needs to be fireproof and also thermally isolated so we don't hurt other organs. The usual fireproof insulating materials are not good here because they are not exactly healthy. Wikipedia glass wool, health problems, and Wikipedia mineral wool, safety of material. So I think what we should do is to create a small version of a thermos which isolates using vacuum and so is not poisonous. So a thermos is a vacuum flask, okay, like you put coffee when you go to a picnic. So a thermos so this would be like a thermos, okay? So we have, okay, this is like a thermos, a mini thermos. The container is actually a thermos. Or a vacuum flask. Okay, but instead of just one opening at the top, we need two controlled openings. One at the top and one at the bottom. Okay, so here we have like, here we have a door that can open or close, okay, like we have here. Here also we have a door. I'm drawing it like this so you can understand, okay. Normally it would look like a thermos, but now I'll draw it like a circuit of electric circuit, okay. So it's like, here you have a door, that can close, and here you have a door that can close. Okay, so when we want to open it, we open it, we let this device come and burn half of the cancer, and we close this so we don't kill all the cancer. Okay, half of the cancer is here in the near the placenta, so we don't want to kill everything. We just want to, this is like a thermos, but with the controlled doors, controlled openings. Okay, like maybe you have a button here and you can press and press. Okay, so but instead of just one opening at the top, it needs two controlled openings, one at the top and one at the bottom. So while the cancer grows into the thermos from the top, we keep the top opening open, and the bottom opening that leads to the appendix we keep closed. And when we want to do the ablation or burning, we close the top opening. Okay, this is like in my description, this is the top. Okay, top. I know it's like should have been here since I drew the thermos like that, but imagine that I drew the thermos towards here. Okay, so so anyway, when we want to burn this, we open this opening, forget the top bottom. We open this thing, we close this, we burn what we need to burn here without damaging this. This is stays, the cancer here is healthy, is okay. Well, it's not healthy, it's a cancer, but it's like living, and here the cancer is dead. And there is a closed door that doesn't let us hurt the cancer that is living. Okay. So Then when we want to do the ablation burning, we close the top opening, and this way we isolate the piece of tumor that we want to destroy from the piece of tumor that we want to leave. And we open the bottom opening through which we can insert the needle-like RFA probe, and we activate the device. Then we take the device out and put in a catheter. Okay, like if you cannot pee, they put a catheter through your urethra. So it's the same thing. It's like which we suck out the remains of the dead cancer tissue like a tiny vacuum cleaner. Can you hear me? Yeah, okay. Also there? Yes, okay. 36 minutes. Then we take out the catheter and restore the doors to normal. Okay, normally this is closed, this is open, and the cancer can grow back to here. It's also here and it's also here. And when we want, we kill it here, but leave it alive here. Okay, so it doesn't get too big. Okay. Another possible way is internal, okay, without penetrating like this. There is a way of doing this internally. Let's explain. Another possible way is internal. So we put a small antenna on the thermos inside, on the thermos inside the body, and connect it to the pyroelectric crystal. Okay, so we have a small antenna. And it's connected to a pyroelectric crystal. So, I don't know what a pyroelectric crystal looks like. Let's make it like a diamond, okay? So, I'm sure it doesn't look like a diamond, but I don't know how to draw it. So, let's make it like this. Pyroelectric crystal. Okay, so that's this thing. So the antenna is connected to a pyroelectric crystal. Then we broadcast radio waves through the body, like putting a special radio on our belly. Okay, so we have here some other antenna that broadcast to this antenna, like from here to here. And this gives the pyroelectric crystal the energy. Then we broadcast radio waves through the body, like putting a special radio on our belly. And then the antenna transforms the radio waves into electrical current. And the current runs through a small wire and powers a thermoelectric generator. This way we don't need the needle-like RFA probe, but we still need the catheter, and we need two insulated wires that will carry the power from an external power source into the body via the navel hole. Okay, so I described it incorrectly. Like we could do this, but we also could do it with wires. So let's do it with wires. So the wires goes into here and give us power. Okay, 2 wires from some battery outside. Okay, so Wikipedia, thermoelectric generator. Making cooler / generator with thermoelectric device by Electro Boom, and I'll give you the link in the description. So see in this nice video, okay, by Electro Boom, he is interested in the cool side. We are interested in the hot side. Okay, so it's like this crystal has one side which is the crystal has 2 sides, one side which is hot and another side which is cold. Okay, so this is the pyroelectric crystal. It's half hot and half cold. We cannot make something like we need to pay. So in the video he's interested in the cold side. He wants to cool something. We want to heat something. So we need to take the coldness away through this wire, through this copper wire. So what do we do with the cool side? We don't want to freeze inner body parts, so we need to conduct the cold temperature through a copper wire, which is an excellent conductor of heat, with insulation, so that again we don't hurt the appendix. We go through into some cool sink outside that can accept the coldness from the wire. It makes no sense to put the thermoelectric device inside the thermos. We should put the hot side attached to the inner side so it hits the entire inner part. Okay, so we don't want, I drew it incorrectly, let's make it correct. Like the thermos should pass here. Okay. Okay, so the cold side is here, but the heat is taken away. Okay. It makes no sense to put the thermoelectric device inside the thermos. We should put the hot side attached to the inner side so it hits the entire inner part, or else we do something and we do the opposite inside the thermos. Okay. So 44 minutes almost. I'll drink something. Okay. Sorry. Now, option 2. In through the appendix. Okay, so that was taking things with the catheter out of the appendix. Now we are talking about in through the navel, through the appendix. Sorry, into the navel and through the appendix and out of the colon. And out of the colon. Okay, so this is option 2. Okay, this option is similar, but works like what we described from Wikipedia about pouring a liquid solution into the navel hole, and the solution washes its way into the colon from there outside the body. Okay, through the colon. The blood plumbing remains the same as we described in option 1. What is different is that the thermos lower opening connects to the colon. Okay, so the thermos, it will be hard for me to draw it, but okay, so instead of I'll read it to you and then I'll try to explain, to draw, okay? So the thermos, what is different is that the thermos lower opening connects to the colon. This makes it super important that we totally killed whatever active cancer cells were inside the thermos, so they don't infect the colon with cancer. The thermos upper opening needs to connect sometimes to the tumor and sometimes to the washing pipe from the appendix, but never both in the same time, so it's or, either or. Okay, so we have okay, so sometimes it connects to what we said, and sometimes it connects to the tumor, and sometimes it connects to the washing pipe from the appendix, but never both in the same time, so it's all. So it's like we have two doors here. Okay, forget the top and bottom because it's confusing. We have this goes to the colon. Okay, to colon when we need to wash things, and we have like a door here that can either close this and open the colon, or close this and then it touches the what we call the appendix. Okay, so it's like that. This door is either here or here. Of course, we can do it with two doors. We can put the door here and the door here if we want. Okay, so the thermos upper opening needs to connect sometimes to the tumor and sometimes to the washing pipe from the appendix, but never both in the same time, so it's either or. So in theory, it's enough to have at the top one door swinging between two openings, okay, here and here. But I think the mechanism would be simpler if we have two separate doors at the top. Okay, so we can have one door here and one door here. Sorry. So we can have one door here and one door here. And this can close or open, and this can close or open. Okay, this can close or open, this can close or open. Let's draw them both like they're half closed because we want to see that they are doors. So this is half closed and this is half closed. So in theory it's enough to have the top door at the top, one door swinging between two openings, but I think the mechanism would be simpler if we have two separate doors at the top, one for each opening at the top, and the bottom of the thermos like before, one door only, this time opening into the column. Something is not clear in my description, but you understand that we want both this. We want to get things from the outside, from the we want to wash. We want to put water through here and wash it once we killed what is here. The cancer is between these two things, and we want to wash it down the colon. So forgive me if I said like top, bottom, and confused the description, but it's like it's supposed to be simple. Coming in, washing to the colon. Okay. So in option 2, we don't use a catheter like a vacuum cleaner. We don't put here a catheter and take out from here. Instead, we use something like a miniature wash bottle, you know, like in the lab that you can squeeze and it squirts water through a nozzle. So you can rinse something. So wash the glass. So we put water from here, from like squirting this and into the dead cells that we killed and to here, to the colon. So in option 2, we don't use a catheter like a vacuum cleaner. Instead, we use something like a miniature wash bottle to hose down the burned cancer cells after we burn them. Sorry, you can see in Wikipedia wash bottle. The disadvantage of my approach is that you need a placenta. Okay, so in any case you need a placenta. But there is no shortage of placentas. Each baby that is born has one, and they throw it to the garbage. You just need to check if it matches the patient, the same as with any organ transplant. Okay, because we put it in the patient's body, like touching the inside of the appendix, so we need to match. Okay. What time is it? 53 minutes. Okay. But in the future, people can keep their own placenta from their own birth in case they need it someday. Like today we keep organs in cryopreservation before transplant. You can see in Wikipedia cryopreservation. Also, it looks like scientists already invented an artificial placenta, or they are close to do this. Artificial placenta analysis of recent progress in Science Direct. I'll give you the link. Artificial placenta created in the laboratory. Okay, this is in Science Daily. I'll give you the link. Okay, so now I'm just talking of like 1 minute about Dr. Judah Folkman. So Dr. Judah Folkman, which my whole invention is based on his work, 1933 to 2008. Okay, so I'll give you a few links in the description. If you want to know more about Dr. Judah Folkman, the father of angiogenesis, which is the basis for my invention, watch this wonderful documentary, Nova, Cancer Fighter. Okay, so Nova, Cancer Fighter. PBS Nova, Cancer Warrior, full documentary in Daily Motion. I'll give you the link. PBS Nova, Cancer Warrior, full documentary 1 in YouTube, and I'll give you the link. And also here is the nice companion website to this documentary, and there is a link to Nova. So that's it. I hope it was clear. I'm sorry it was rushed, and this was my invention, and I'll see you in my next invention. So thank you very much. Goodbye. Thank you.